So guys, welcome to yet another course of CSE Practicals. In this course, we will going to implement access control list and routing tables in C and C++. As we know, access control list is a feature that is used extensively in the networking equipments, and access control list is used to implement the security, control the traffic flow, or controlling the access to certain devices in the network. Whereas routing tables has only one use case, and that is forwarding the traffic. So in this course, we will going to implement and design the data structures which implements the access control list as well as routing tables. We have chosen to club these two together in one course because the data structure that we will going to implement is a common data structure that is used to implement ACLs, that is access control list and routing tables. We will going to end up designing and implement only one data structure, but that data structure could be used as a routing table as well as to implement access control list. Needless to say, the data structures are not trivial. They are a little bit complicated data structures, and hence we have decided to come up with a different course altogether on this topic. It is very commonly asked to experienced developers to come up with the data structures which implements the routing table operations or as well as access list operations. As we know, routing table and access control list are one of the most common features supported by the networking equipment such as routers or switches in order to implement the data forwarding or security. So prerequisite of this course is nothing but you need to be just a very good C or C++ programmer. If you are a programmer in different language such as Java or C#, then also you can very much follow up this course. I will going to explain the concepts, and it is up to you how you implement those concepts. This course is exclusively for developers. So if you are not a developer, so you may please excuse this course. Almost all my courses are designed for developers only. So you can browse my course catalog and see what is there for you that you can learn from. And the level of the students that is required to do this course is from intermediate to advanced, because this course would going to be algorithmically challenging. So this diagram shows the roadmap of this course. In the phase 1, we will going to implement the bitmap library. In the phase 2, we will going to implement mtry library. So mtry is a data structures which we are looking to implement eventually. This is our main target. And in order to implement mtry data structures, we need supportive libraries or supported data structures such as stacks, linked list, and bitmaps. Once in phase 2, we will be done with the implementation of our mtry data structure. Then we can use this mtry data structure in order to implement access control list as well as IPv4 routing tables. Alright, so this is the roadmap. First, we will going to implement the prerequisite library, which is a bitmap library. A bitmap is nothing but it is just an array of bits and nothing else. And along the way, we also need the stacks and linked list basic data structures to supplement or support the implementation of our mtry library. And eventually, when our mtry library is ready, then we will use this mtry library in order to implement the access control list and IPv4 routing table. So phase 3 and phase 4 is eventually the final product of this course. Since this course is for intermediate to advanced developers, therefore this course is fast-paced. There would not be any spoon feeding. I expect that developers are in a position to implement the stuffs on their own once they are provided or equipped with the sufficient knowledge or background regarding what exactly needs to be implemented and how. So this is the roadmap for this course. Then coming to the discussion of certain prerequisites. Since you are signed up for this course, I assume that you already are aware what are access control list and what is their use cases. And I expect that you already know what are layer 3 routing tables and what for they are used for. If you are hearing these names, that is access control list or L3 routing tables, for the first time, then please excuse this course. This course isn't for you. You have more homework to do, that is first get yourself aware what are access control list and what are routing tables before jumping into implementing these data structures or features. You have good coding skills in any mainstream language. So in this course, I will going to present you all the code demonstration in the language C or C++. But you can very much do this course provided that you know the prerequisite, that is the access control list and layer 3 routing tables, plus you are good in coding skills in any mainstream programming language such as Java, C#, Python, etc. It is up to you that in which language you want to implement this course. And this is advanced course, so obviously there won't be any spoon feeding. I have courses which are pretty much basic courses and for beginners or for those developers who are at the beginning stage. So in this course, I usually try to explain things from absolute scratch and in pretty much detail. But for the courses which are actually designed for somewhat developers who are at the advanced level or who are just above the intermediate level, I usually don't do any spoon feeding kind of stuff. I usually go fast in such courses. And you will be writing lots of code by yourself. This course is pretty much for any engineer who is working in the networking domain, in the cloud domain, or in the distributed systems as a developer. And for this course, you are very much required to understand what are subnet masks. So if you have a little bit of networking background, you would know that what exactly subnet masks are. All right. If you don't know what masks are and how does it work, then again, it is a prerequisite knowledge to know and it is mandatory. If you are not aware what masks are, how does it work, what is the role of masks in the networking, then probably you are signed up with the wrong course. And I also assume that you have a fair debugging skill. For example, you know how to run GDB or other debugging tools. You know how to work with integrated development environment, that is IDEs, etc., etc. In this course, you would be writing a lot of bit manipulation code. So obviously, if you do any programming error, then debugging that error would not be very straightforward, because in this course, you will be going to write a code in which you will be dealing with bits. So you need to be good at programming at the bit level. And finally, the takeaway from this course is that you will not only able to explain, but also would be in a position to implement access control list or routing tables. In this course, I would going to show you the implementation of both of these data structures. In fact, the end product of this course is that you will be able to come up with the generic library which would act as an object filtering framework. You just feed the set of rules in that library that on the basis of what rules you want to filter the input objects. Then the final data structures, which is the end product of this course, can also be tweaked slightly in order to implement Linux user group permission framework. Or you can also implement Linux IP tables like software. All right. All of these features more or less are same in terms of functionality, and therefore the implementation of all these features behind the scenes require more or less the same type of data structures. So once you are equipped with the knowledge regarding how to design access control list or routing tables, you would be in a position to enhance the final product of this course, that is the mtry library, to implement object filtering, Linux user group framework, or Linux IP tables like software. All right. So good luck, guys. Keep learning and join us towards progressing towards becoming a 10x developer in your career. So guys, in this section, we will going to revisit ACL and routing table data structures and how do they work. So in this section, we will going to cover the basics. If you already know, or if you already have enough knowledge regarding how access control list work and how routing table works, then you can safely skip this entire section. In this section, I will only going to cover the basics, explaining that at the most basic level how access control list and routing table works. So if you already belong to the networking industry and have sufficient knowledge, then you can safely skip this entire section. So access control list, which we often call as ACLs, are nothing but set of rules with the verdict either permit or deny. So set of rules means a rules which says that either something is permitted or something is denied. ACLs or access control list is used in many real-world softwares and products. In fact, ACLs are extensively used in the networking equipments, which could be firewalls, routers, or switches. All right. So now let us discuss one real-world example of access control list. So here is a sample configuration of access control list, and exactly same format is specified on Cisco devices. So I have shown the access control list whose name is block traffic. So note that access control list have names. In this case, I have chosen a name, block traffic. And this is one access control list with 2 rules in it. So remember, access control list is a set of rules. And here you can see that it is exactly one access control list whose name is block traffic, but this access control list contains 2 rules. This is the rule number 1 and this is the rule number 2. All right. And this is exactly Cisco format. If you have an experience of working on Cisco switches, routers, or firewalls, so ACL rule, so these individual lines in the access control list are called rules, and we call them as ACL rules. All right. So ACL rules have a fixed format. The ACL rule starts after the name of the access control list. So this is the starting point of the ACL rule. So ACL rule says that what is the decision, that is permit or deny. So the decision could be either permit or deny and nothing else. All right. The first parameter is the protocol. The second is the source address and source mask, which you can see in this example. And after that, you can specify the destination address and destination mask, which is optional. In fact, the source address and source mask is also optional. You can have an ACL rule which says permit or denied, including the protocol only. So specifying the protocol is a mandatory. After that, everything is optional. So once the packet arrives into your box, and if you have access control list configured, you extract the destination address, a source address, and the protocol value from the IP header of the packet. And once you have the protocol, the source address, and the destination address extracted from the IP header of the packet, you evaluate these parameters against the access control list and see whether these combinations of parameters passes the access control list or not. All right. Now passing the access control list means that exactly which ACL rule these parameters passes. These parameters will be evaluated against the individual ACL rules, and it could be possible that ACL rule 1 may say deny, but the ACL rule 2 may say permit. All right. So we will going to understand that exactly in what order the 3 parameters, the protocol, source address, and destination, are evaluated against the individual ACL rule of the access control list. It is not necessary that they will be evaluated in the top-down order. It is not necessary. User can configure the ACL rule in any order. We will see shortly that these ACL rules are evaluated against these parameters of the packet in the longest prefix match order. Now what is that? We will going to discuss shortly in the next lecture video. So for now, the takeaway from this slide is that how to specify the ACL rules. Each ACL rule is tied with a verdict, which is either deny or could be permit. And every ACL rule has a fixed format to specify. That is the permit followed by protocol, followed by source address and mask, followed by destination address and mask. The access list has a name, and access list is a collection of ACL rules. So now in the next lecture video, I will show you that how the parameters from the IP header of the packet are evaluated against the access list. So guys, now let us discuss an example in which we will going to see that how the parameters from the packet are evaluated against the configured access control list which the user has configured on a device. So let's say that the user has configured an access control list whose name is allowed traffic, and in this access control list the user has configured 4 ACL rules. Alright. Now let us suppose that an IP packet number 1 came in which in the IP header of the packet the protocol field value was UDP, the source address of the packet was 122.1.1.2 and the destination address of the packet is 50.1.1.1. So as soon as this packet is injected or arrived at the routing device, this packet is evaluated against the configured access control list. Alright, and this access control list would gonna say whether the packet is permitted or denied. Now if you evaluate these 3 values of the packet against the access control list, you will find that it is the rule number 2 which actually says that the packet is permitted. Rule number 1 doesn't matches with the source address of the packet, and the rule number 2 matches the source address of the packet as well as the protocol field value. The protocol field value you can say is UDP, and 122.1.1.2 is an address which belongs to this subnet address. So it means that the rule number 2 matches with the 3 parameters of the packet. Obviously in this access control list you have not specified any destination addresses in any ACL rule. It means that we don't care regarding matches the destination address from the packet with the destination address and mask value configured in the ACL rule. In other words, any field which is not specified in the ACL rule is taken as don't care. That is, always assume that those field matches with the fields belonging to the packet. So destination address 50.1.1.1 always matches with every ACL rule in this access control list. Alright, because none of the ACL rule specifies the destination address. Now if you notice, these 3 parameters of the packet when evaluated against the ACL rule number 3, you will see that even the ACL rule number 3 says that the packet is permitted, because this source address of the packet also belongs to this subnet mask, and the protocol field value of the packet matches with the protocol field value specified in the ACL rule number 3. So it means that for the IP packet number 1, both the ACL rules, that is ACL rule number 2 and ACL rule number 3, both says permit. So now the question is that which ACL rule we must honor. Should we announce that the ACL rule number 3 has permitted the packet or the ACL rule number 2 has permitted the packet? The answer is simple. We will say that the ACL rule number 2 has permitted the packet because ACL rule number 2 is more specific as compared to ACL rule number 3. You can see that the subnet mask value in the ACL rule number 2 is more specific as compared to the subnet mask of the source address specified in the ACL rule number 3. In other words, ACL rule number 2 is more specific, whereas ACL rule number 3 is more generic as compared to ACL rule number 2. So we always pick up the most specific ACL rule in case if there are multiple ACL rules, which matches the 3 parameters of the packet. And this concept is called longest prefix match. We will see when we will going to discuss the algorithm in detail regarding the access control list implementation, that actually how we implement the logic such that always the longest prefix match ACL rule is selected over other ACL rules in the access control list, which also matches with the 3 parameters of the packet, but those ACL rules are more generic. So for IP packet number 1, we can say that it is the ACL rule number 2, which says that the packet is permitted. Permitted means the device is ready to accept the packet for further processing, and it will not drop the packet straight away. Similarly, when the IP packet number 2 arrives, and let's say that the source address of the packet is 122.1.1.1, so it is the rule number 1, which is the best match as per the 3 parameters of the packet. So we will say that the IP packet number 2 matches with the rule number 1 of the access list, and hence the packet is permitted as per the verdict of the rule number 1. You can see that the IP packet number 2 also matches with the rule number 2 as well as rule number 3, but it is the rule number 1 which is the most specific. You can see the source address is exactly says that the source address should be 122.1.1.1 as per its subnet mask value. Alright. Similarly, when the IP packet number 3 arrives, you can see as per the access control list configuration, none of the rules of the access control list matches with the 3 parameters of the packet. Alright. In fact, it is the source address which do not matches with the source subnet of any of these ACL rules. And it is the rule number 4 of the access control list which actually matches with the 3 parameters of the packet. Alright, the protocol field value is any, so it means that UDP will going to match with this protocol field value. The source address says 0/0, it means any source address. So if you are aware that how subnet mask works, the 0 IP address coupled with the 0 mask value means any source address. So here any source address of the packet would match the ACL rule number 4. Alright, and as per the verdict of this rule number 4, the packet will be denied. So this packet will be dropped by the device and will not be considered for further processing. So packet number 3 is discarded because it matches with the rule number 4. So here many rules in the access control list may match the given input. As I said, the packet number 2 matches with the ACL rule number 1, ACL rule number 2 and ACL rule number 3, but we care only for the best match rule. So it was the rule number 1 which was the most specific, and it was the rule number 1 which was considered as the rule which matches the packet number 2. Any field which is not specified by the user in access control list rule is taken as don't care field. So you can see we have not specified destination IP address and mask against any of these ACL rule. So it means that they are don't care. Do not bother about matching the destination IP address from the packet with the destination IP address and the mask value specified in the ACL rule. So they are implicitly programmed as don't care in the data structure. And guys, let us discuss another example. So we have an access control list here which contains 4 ACL rules. Now in these ACL rules, I have also added the destination IP address and mask as another field for filtering. Now suppose the IP packet number 1 comes. So the rule that matches as per the longest prefix match is nothing but the rule number 4. The reason is that this is a destination IP address which do not matches with the ACL 1, ACL 2 and ACL 3, and hence ACL 4 is the most generic ACL which in fact would match with any set of parameters of the packet. So IP packet 1 will match with the rule number 4, IP packet 2 will match with the rule number 2, and IP packet 3 will match with the rule number 4 again. Alright. So if you want to understand more about access control list, or if you are curious to know more about the access control list, you can always go to the YouTube and type search the access control list. It's a very common topic of discussion in networking, and hence you will find lots of videos on access control list. However, this course aims at implementing the data structure which implement access control list. So a basic knowledge regarding how access control list work is more than enough in order to accomplish this course. And guys, going forward, now let us see that how a typical router or a layer 3 forwarding device does routing using IPv4 routing table. So layer 3 routers needs a routing table to decide where to forward the network packet. The routing table also works on the principle of best match, also called as longest prefix match. So let us suppose that we have a sample routing table here, and let us suppose that there are certain set of packets which arrives at the router with the following destination IP addresses in the IP header. Alright. So if the destination IP address is 1.1.1.1, which of the following routes in the routing table will be used to forward this IP packet? The answer is, based on the longest prefix match, the route number 3 will be used because it is the route which matches best as per the longest prefix match principle with the destination IP address 1.1.1.1. So there is a general formula. Use this algorithm to determine whether a given IP address matches with the given route or not. You take the input IP address. In this case, I took 1.1.1, that is this one. This is the input IP address. Then take the subnet value of the route, which is 32. Of course, you need to express these values in the binary form. And then take the destination IP address of the route, which is 1.1.1.1. All right. Now you perform the ORing of the input IP address and the subnet value. The answer that you will get will be 1.1.1, which is equal to the destination IP address. So if this equality holds, it means that the given IP address matches with the given route. However, this doesn't say that this particular route is the best match for this IP address. It only says that this is the route which matches with the given destination IP address. Similarly, if you apply the same algorithm with the route number 2 and the destination IP address 1.1.1.1, it will also match. And if you apply the same algorithm with the route 1 with the destination IP address 1.1.1.1, then again it will match. In fact, these are the 4 routes plus the default route which actually matches with this destination IP address as per this algorithm. Alright, but we are interested in choosing a route which not only matches with this destination IP address but also has the longest prefix match among all the routes. So such a route is the route number 3. So it means that the route number 3 will be used in order to forward all the packets with the destination IP address 1.1.1.1. Similarly, if the packet with the destination IP address 2.1.1.1 comes, then the route which will be used to forward such a packet will be the default route, that is route number 7. There is no other route in this routing table which matches with this destination IP address as per this algorithm. Similarly, if the packet comes with the destination IP address 1.1.4.5, then the longest prefix match based route will be the route number 2, which will be used to forward this packet. And for the packet with destination IP address 3.0.0.0, obviously the default route, that is route number 7, will be used to forward this packet. Alright. So the idea of this lecture video is to tell you the concept of longest prefix match in case of forwarding of IP packets using IPv4 routing table. So all this is a prerequisite knowledge of this course. It is expected that you know the concept of longest prefix match when it comes to the forwarding or when it comes to the filtering using access control list. This section is just a revision regarding how ACLs and layer 3 forwarding happens using the concept of longest prefix match. Our emphasis is on longest prefix match because the data structure that we will going to design would going to respect this property. So guys, to put together what we have covered in this course so far, access control list and routing tables works the same way. Both works on best match principle, which is also called longest prefix match. Both needs to work with wildcard bits, which is a method of representing don't care bits. Alright. So the common interview questions for 4 to 5 years experienced would be, what's the data structure to implement routing table? It's an open-ended question and the entire interview process can revolve around this question. Then another question could be, explain the design for implementing access control list. All right. So these are the common interview questions that could be asked, provided that you fall in the domain of networking or in some domain where routing table or access control list is used extensively. So guys, now let us start with the discussion of data structure and algorithm required to design and implement routing table. So before going forward, let us make ourselves familiar with some keywords. The keywords are prefix, mask, and wildcard. So let us get ourselves familiar with the definitions of these keywords. So let's say you have an IPv4 route as an example, which is 1.2.3.4/24. So with this example, the prefix is nothing but the actual IP address itself. So here the prefix is 1.2.3.4, and when this prefix is represented in the binary form, you will get 32 bits. This is the first octet, this is the second octet, this is the third octet, and this is the fourth octet. Here octet means a byte. Alright. So prefix is nothing but the actual IP address part of a route is the prefix. Then mask is the 24. In A.B.C.D or CIDR notation, we express the mask as 255.255.255.0. This 24 actually means that the first 24 bits in the binary representation of the mask is 1, whereas the last 8 bits would going to be 0. Alright, so when we say /24, it means that the first 24 bits of the mask are all ones. And of course, the mask length is always 32 bits and the prefix length is always 32 bits. This length is fixed and constant for IPv4 addresses. Then comes the wildcard, which is exactly opposite of mask. If you flip the bits of the mask, then you get the wildcard, as simple as that. So in CIDR notation, the wildcard is expressed exactly opposite to that of the mask. That is, you replace 255 with 0 and you replace 0 with 255 and so on. In the binary notation, all the ones will be converted to 0 and all the zeros will be converted to ones. So this is what wildcard is. Alright. Then comes the effective prefix. Effective prefix is nothing but you are trying to view the prefix and the wildcard as one single logical thing. So in effective prefix, you take the bits from the prefix and you take as many bits from the prefix as equal to this mask number, which is 24. So you have taken 24 bits from the prefix and the remaining bits will come from the wildcard. So in a wildcard, in whatever positions you have 1, just replace those 1 and represent those 1 by X. So here X represents don't care. Alright. So in the wildcard, at those bit positions where you have 1, those bit positions are don't care. And in the mask, those bit positions where you have 0, those bit positions are don't care. So you have don't care both in mask as well as wildcard. The only difference is that in the mask, don't care is represented by bit 0, whereas in wildcard, it's the bit 1 which represents don't care. In effective prefix, the don't care is represented by a symbol X. So note that effective prefix is used to view the prefix and wildcard together for easier human understanding purpose only. To store the effective prefix in computer memory, you still need a prefix and wildcard together saved in separate variables. Alright, so in a separate variable, you store the prefix part, and in separate variable, you store the wildcard part. And combining these two, you will get the effective prefix. Alright. So in the remaining part of this course, we will going to keep on saying the word prefix, the wildcard, the effective prefix. So it is important that you get familiar with the vocabulary that we will going to use in this course. And you can see here is some URL, which is nothing but it is a nice IP calculator present online. You can always use this calculator in order to convert the IP routes into its binary form and vice versa. So this calculator will help you a lot, and you can bookmark this calculator in your browser. So guys, before we start discussion of our algorithm for implementing IPv4 routing table, we need to get ourselves familiar with certain representations that we will going to follow. So as I said, we will going to use mtry data structure in order to implement routing table, and mtry is a tree-like data structure. So obviously mtry will going to have nodes. We will call those nodes as mtry node. All right. So this is a diagram which shows a typical mtry node which will be used to store routes. So each node of an mtry will going to store route. So let us discuss with the help of an example that how each node in an mtry will going to store information. So let us suppose that we have a route 1.2.3.4/24. So we will going to express this route in terms of prefix and wildcard. And obviously for IPv4 routes, the prefix len is 32. So following is the effective prefix that we will going to derive from the prefix and wildcard combination. All right. So as I said, each node will going to store the information regarding route. Each node will going to store the effective prefix, the prefix len, and certain pointers which points to its child nodes. The child nodes we will going to discuss later when we will actually discuss the algorithm. So the mtry node which will be used to store this particular route would look something like this. This is the effective prefix. This is the prefix len. All right. Similarly, if I have a 16-bit prefix and a 16-bit wildcard, then the effective prefix would be this one. And the mtry node that we will going to store this information would have 16-bit effective prefix, and this is the prefix len. All right. Now note that each mtry node may store a part of the route or the entire route altogether. There is no restriction. So now if I were to ask you that, can you write a data structure definition which represents an mtry node optimized for storing routes? So you would say that this is such a data structure. As I said that each mtry node would going to store effective prefix, and effective prefix is stored as a combination of prefix and wildcard. Therefore, you would need two bitmaps in order to store prefix and wildcard separately. But together they represent an effective prefix. All right. Bitmap is nothing but you can visualize bitmap as an array of bits and nothing else. All right. Prefix len we already know. In this case the prefix len is 32. In this case the prefix len is 16. So number of bits in the prefix and total number of bits in the wildcard is the prefix len, and prefix len of the prefix and wildcard is always going to be same no matter what. All right. Then each node contains a pointer to the parent, and each node contains the pointer to its children. This we will going to discuss when we will be actually discussing the algorithm. Each node also contains some data which we will going to discuss when we will be discussing the algorithm. All right. So the point here is that you should understand the mtry node data structure and how we will going to store the effective prefix in this data structure as well as the prefix len. And finally, we need to discuss how to represent the root of the mtry. So as I said, mtry is a tree and every tree has a root. In our case, our mtry data structure has a root which is actually a special node in the mtry and differs from rest of the nodes in the mtry. So root of the mtry will going to be a special node, and we need to discuss that. So this represents the root of the mtry, and the special thing about root is that it do not have any effective prefix and its prefix len is 0. So it means that this particular bitmap will contain all zeros, and the wildcard also contains all zeros. The prefix len will be 0, the pointer to the parent will be null. And to initialize with, in the beginning, when the tree is entirely empty, all the child nodes would point to null. Alright, and the data part is also null. So this is what root node is, and this is what mtry data structure would look like when the mtry data structure is just initialized. A freshly initialized mtry data structure will just contain a root node with everything initialized to null or 0. Alright, now coming to this enumeration, as I said that each mtry node will going to have 3 children. These children are indexed in the mtry node as 0, 1 and don't care children. Alright, we will going to discuss in detail when we will going to discuss the algorithm that what does it mean by saying that this particular children is a 0th children or 0th child, or this particular children is a 1th child, and this particular children is a don't care child. So each node in the mtry can have maximum of 3 children, and we index these children as 0, 1 or don't care. And as I said, you need to visualize bitmap as an array of bits and nothing else. And on this array you can perform operations like you would have performed on normal arrays. For example, we can implement a function bitmap set at, pass the pointer to the bitmap and pass the index. So for example, if you pass the index number as 18, then this particular function must set the bit at index 18 to 1. Alright. So guys, with this we have finished with all the prerequisite details that we need to know before we start our discussion on implementation of IPv4 routing table. First, we will only going to focus on the algorithmic part, that is how we will going to insert routes in this mtry, how we will going to delete the routes from this mtry, how we will going to search for routes in this mtry, and how we will going to implement longest prefix match based search in this mtry data structure. Remember, this mtry data structure would be nothing but it is your IPv4 routing table in the end. So I hope you understood this structure. This structure is very much important in order to understand the algorithm. Once again, every node of the mtry will going to store the effective prefix, which is a combination of the prefix and wildcard, of course, the prefix len, the pointer to the parent, and the pointer to its children, and the additional application specific data. So now in the next lecture video, we will going to start our discussion with how we will going to insert routes one by one into a mtry data structure. So guys, now let us start with understanding of the algorithm to construct IPv4 routing table. So to start with, we have a root node of the mtry, and the root node initially is empty. It do not have any effective prefix. The prefix len is 0 and all the pointers of its children are null. Here 1 represents the node ID. So I have taken a node ID only for the sake of making our discussion a little bit easier so that I can talk about that this node and that node with the help of node ID. Otherwise, node ID has nothing to do with the algorithm. It is only for the sake to identify that which node I am talking about. So to start with, let us say that we need to insert a route 1.2.3.4/32. Alright. So the very first thing that we need to do is to convert this route into its effective prefix form. So this is the effective prefix for this route. Alright. And when we say route, it also means that you are also saying that when this route is used for forwarding the traffic, then which is the next hop to be used? So next hop is some data structure which is in memory somewhere else. Alright. And we call the data of this route as that next hop, that is the address of that next hop. So every route is associated with the next hop, and the data part is nothing but it is the next hop object which is associated with that route. All right. So the next thing that we need to do is to insert this route into our mtry data structure. So insertion of the route always begins from the root. Now in order to insert a route, we will going to examine the very first bit of the effective prefix bit of a route. In our case, the very first bit is 0. All right. So it means that we need to insert this route as a 0th child of the root node, and it's over. All right. So the new node that is just inserted has been given a node ID, say 2. And because the effective prefix of this route started with bit 0, so we will going to insert this particular route as a 0th child of the root node. So for the node 2, this is the effective prefix, this is the prefix len, and this is the data part. And obviously all the children of the node 2 will point to null. And now the 0th child of the root node points to the node 2. All right. So with this, the insertion of this route is successful. Similarly, if you want to insert the route 128.234, quickly convert this route into its effective prefix form. So this is the representation of this route. And examine the first bit of this route, which is 1. So again, the insertion of the route begins with the root node. So we will going to create a new node with node ID say 3, and we will make this new node as the 1th child of the root node. And the node number 3 will going to contain the effective prefix as the following, and this is the prefix len, and this is the data part. All right. So we have successfully inserted the route number 2 in this mtry data structure. So things are pretty much easy and simple. We just scan the first bit of the effective prefix of the new route, and based on that, we insert a new child node as a child of the root node. Similarly, suppose you want to insert the route number 3, which is a default route, 0.0.0.0/0. So the effective prefix representation of this route is nothing but all don't cares. All right. So the first bit of this effective prefix is don't care. So it simply means that you need to insert a new child node as a don't care child of the root node. All right. So for the node number 4, the effective prefix is the following, and the prefix len would be 32, of course, I missed it. And the data part will point to the next hop of this route. So far the things are pretty much easy and simple. Now let us talk about insertion of the route 128.2.0.0/16. All right. So now things becomes a little bit non-trivial. So let us convert the route number 4 into its effective prefix form. So you can see this is the route number 4, which is converted into its effective prefix form. Now let us start traversing the tree starting from the root node. So the first bit of this new route is 1. So we will traverse the child number 1 of the parent node. So we reach the node number 3. And once we descend down the tree, we do the prefix matching. So we will going to match the effective prefix of the node 3 with the effective prefix of the new route, and we find that the first 16 bits of the node 3 matches exactly with the first 16 bits of this new route of the effective prefix, of course. So it means that the bit which is highlighted in pink color is the bit at which the mismatch happens. So whenever in the route insertion a mismatch happens, like this case, the node present in the mtry at which the mismatch happens will undergo node split. So it means that the node number 3 will undergo node split procedure. Now what is node split procedure? Let us discuss that. So guys, now let us discuss how node split procedure is executed. The node number 3 will undergo node split because while traversing down the mtry from the root node, at node number 3, there occurs a mismatch in the effective prefix of the node 3 and the effective prefix of the new route. The bit at which the mismatch happens is shown in the pink color. Alright? So this is the point at which a node number 3 will undergo node split. So as a part of node split procedure, the very first thing that we do is that we will going to create two new nodes. The node number 5 and the node number 6. The node number 5 is called a daughter node, whereas node number 6 is called a niece node. Now node number 5 is called a daughter node because as a daughter of its parent, the daughter node will borrow the possessions of its parent node. Now what are those possessions? First of all, the daughter node will borrow the bits from the effective prefix of its parent node. From the point where the mismatch has happened up to the last, all the bits from the effective prefix of the parent node is copied as it is as the daughter node effective prefix. So actually it is not a copy, but it is a transfer. So as we are transferring here 16 bits from the parent's node effective prefix to the daughter node effective prefix, therefore parent node effective prefix would be shrinked by 16 bits. So the new prefix length of the parent node would become 16 because the latter part of the 16 bits has been transferred to the parent node. Alright, so the parent node's prefix length would become 16. This is the first thing. Now why we have made the daughter node as the 0th child of the parent node? Because the bit at which the split happens is the 0th bit. Alright, so it means that the daughter node will become the 0th node of the parent node. Then daughter node also borrows the data of the parent node. So whatever be the data pointer of the parent node was, the daughter node will borrow that data. Alright, so the data pointer of the parent node would become null. And the third thing that the daughter node borrows from the parent node is the children of the parent node. So in this case, we did not have any children of the node number 3 before the node number 3 undergo a split. But if it had any children, all those children will be transferred to the daughter node. So we will see this procedure when we will going to split the node which already had children in our subsequent example. So this was the story of the daughter node. The daughter node borrows 3 things from the parent node. The first is the bits from the effective prefix of the parent node. The second is the data of the parent node. And the third is the children of the parent node. Alright, and obviously the prefix length of the parent node would get reduced after a split depending on how many bits have been transferred to the daughter node. Then the second node is the niece node, which is very simple case. The niece node will borrow its effective prefix bits from the effective prefix bits of the new route. Right? So from the point where the mismatch has happened, we will going to copy the prefix bits of the new route as the prefix bits of the niece node. And here, since we are copying the 16 bits, therefore the prefix length of the niece node is 16. And obviously the data part of the new route will be copied as it is as the data part of this niece node. And obviously, since the niece node is a new node, all of its children points to null. And why this niece node is made as a don't care children of its parent? Because the first bit of this niece node is a don't care. So this is the procedure of splitting a node. You can rewind this video and go through the explanation again to understand it better. However, we will going to insert few more routes in this tree and we will going to discuss node split algorithm few more times again. So the following points needs to be highlighted. Data of the parent node is transferred to the daughter node. Transfer of the effective prefix bits of the parent node to the daughter node. And transfer all the children of the parent node to the daughter node. Alright. So you can see that the daughter node is notorious in the sense that it takes away all the positions of its parent node, which is undergoing a split. Remember that. So the next slide shows that how does the mtry data structure looks after the insertion of the route 128.200/16. This is the pictorial representation of the mtry data structure before the insertion of the route, and this is the pictorial representation of the mtry data structure after the insertion of the route. And you can see all the changes has happened in the node 3 and downwards. The node 2 and 4 of this mtry data structure is untouched. You can see the data part of the node 3 is null. The prefix length of the node 3 has been reduced from 32 to 16. The bits from the effective prefix of the node 3 has been transferred to its daughter node. And the niece node borrows its effective prefix bits from the bits of the route which is just inserted. So now, can you write the steps regarding how the node split algorithm can be written in simple plain English words? Can you do that? Let us do that in the next lecture video. So guys, now going forward, I have enumerated here the route insertion algorithm. I request you to go through these 6 steps of route insertion algorithm and try to relate that we have actually exercised all these 6 steps in the examples so far we have discussed regarding route insertion in the mtry data structure. Alright. Nevertheless, we will going to discuss one more example of route insertion in the mtree. So far our mtry data structure has taken the following shape as you can see on the screen. And now the next route that we will going to insert is the route number 5. Alright, so we will going to insert the route 128.128.0.0 and the mask value is 16. So obviously we will going to convert this route into its effective prefix form. So as you proceed towards inserting this route into this mtry data structure, we start our traversal from the root node of this mtry data structure. Alright, so the very first bit of this new route is 1. So it means that we will going to take the path along the 1th child of the root node of the tree. And we land at node number 3. And now we start comparing the effective prefix bits of the new route with the effective prefix bits of the current node in the mtry. So you can see that the first 8 bits of this node number 3 matches with the first 8 bits of the new route, but the mismatch happens at the following bit, that is bit 0 in the node number 3 and the bit 1 in the new route. Alright, so the node split algorithm will be triggered again at node number 3 and the split will happen on this bit 0 which is highlighted in pink color. So once again the node split algorithm will be triggered at node number 3, and as per the algorithm we immediately create 2 new nodes, the daughter node as well as the niece node. So let's say this time the daughter node is the node number 7 and the niece node is the node number 8. As a part of the algorithm, all the children of the node which is undergoing a split is transferred to the daughter node. Alright, so it means that the node number 5 and node number 6, which are the children of node number 3, will be transferred to the node number 7. And as it is, it's just a plain copy paste. If you had more nodes which are the descendants of the node number 5, then those nodes would have also moved as it is, being the descendant of the node number 5. So in fact here we are transferring the entire subtree which is rooted at node number 5. So when I say moving the children, that is node number 5 and 6, it simply means I am moving the entire subtree which is rooted at node number 5 and the entire subtree which is rooted at node number 6 from the node number 3 to node number 7. Alright, So remember that we are just not moving the children, we are moving the entire subtree. Now the next thing that would happen is transferring the bits from the effective prefix of the node which is going under a split. So these many bits, that is starting from the mismatched bit up to the last bit, all the bits in the effective prefix of the node 3 will be transferred to the daughter node. Alright, so these 8 bits will be transferred to the daughter node, and the parent node 3 will remain with the following bits which are left over. So it means that node number 3 would left with the following effective prefix, and the length of the effective prefix would be reduced from 16 to 8 because the remaining 8 bits has been transferred to the daughter node. The data of the node number 3 before split was null. Therefore, copy the data from the parent node to the daughter node. The daughter node data would also be null. And finally, copying the bits from the input route, starting from the mismatched bit up to the last bit, we will simply copy all these bits as the effective prefix bits of the niece node. Alright, and the niece node is made the 1th child of its parent because its first bit is 1. And the daughter node is made the 0th child of its parent node because its first bit is 0. So we have successfully executed the insertion of the route 5 in this mtry data structure. Alright, so it is the node 3 which will undergo split again, and it will give birth to the new node 7 and node number 8 in the mtry. So if you want to see one complete tree, the following is the tree which would be created after insertion of 5 routes that we have discussed. So this is the final tree, and tree keep growing as more number of routes are added to the tree. Alright, so node merge happens and tree shrinks when the routes are deleted. So we will going to discuss route deletion algorithm in detail, and having understood the route insertion algorithm, the route deletion algorithm would be a cakewalk. The route deletion algorithm would be exactly opposite to the route insertion algorithm. So in this mtry data structure which you can see on the screen, we have inserted these following 5 routes. And you can see that in this mtry data structure we have 5 leaves. You will have as many leaves as many routes you have inserted in this mtry data structure. So node number 2 is leaf, node number 4 is leaf, node number 5 is leaf, node number 6 is leaf, and node number 8 is leaf. The path from the root node to the leaf node represent exactly one route. Alright. Next we will going to discuss the route search algorithm. Route search algorithm means that in this tree we know that we have already inserted 5 routes. What if I tell you that, hey, tell me whether the route 128.2.0.0/16 is present in this mtry or not. So you have to come up with the yes or no answer that whether the route is present or not. As simple as that. So that is called route search algorithm, and not to be confused, it is not a longest prefix match algorithm. Alright, I am simply telling you that given a route, search whether this route was inserted in this mtry data structure or not. So that is the route search algorithm which we will going to discuss next. So guys, with this we have completed the route insertion algorithm, and as a part of exercise I would suggest you that you try to draw your own mtry data structure and see how does the mtry data structure transform when you insert the following routes in this already constructed mtry. Alright, and the time complexity of inserting a route in this mtry data structure is order of k, where k is the number of bits that you are inserting. So for IPv4 routes, k is a constant which is 32. So in other words, the time complexity of inserting a route in this mtry data structure is order of 1. So guys, now we are well versed with the route insertion algorithm, and now we know that how mtry data structure takes the shape as we keep on inserting more routes into this mtry data structure. So now let us go through some point of analysis. So now we know how route insertion happens in the mtry data structure. For every new route that is inserted, 2 new nodes are created, and those 2 new nodes are called daughter nodes and niece nodes. However, there is an exception when you insert a route which is directly hanging off the root of the mtry data structure. In that case, there is only 1 node created and there is no niece node at all. Path from the root to the leaf gives 1 specific route. So this is a tree in which 5 routes were inserted, and if you analyze, if you walk this tree from the root to any leaf along any branch of the tree, each path from the root to the leaf is specific to 1 route. Alright? For example, if you follow this path, then you will encounter the route 128.2.3.4/32. Alright? If you follow this path, you will encounter the route in the leaf, which is 128.128.0.0/32, and so on. Only leaf node contains data. Internal nodes data is always null. So you can analyze in this M tree, all the internal nodes have data equal to null. So you can see this is the internal node whose data is null. This is the internal node whose data is null, whereas the data of the leaf node can never be null. Alright? All internal nodes have exactly 2 children, except root, which can have 3 children. So you can analyze that each internal node exactly has 2 children, and apart from that, there are leaf nodes which has no children at all, and the root node may have 1 children, 2 children, or 3 children, depending on whether you inserted the route whose starting bit was 0 or 1 or don't care. There are no half nodes in the tree. Half nodes are those nodes which have exactly 1 children. So you can see there are no half nodes in the tree when only the route starting with 1 particular bit, that is either bit 0 or bit 1, was inserted in this mtry data structure. In such a case, the root node would become a half node, but apart from the root node, no other node in this mtry data structure can be half node. Alright? Sum of the prefix length from root to leaf along any branch is always 32. So you can see, let us suppose that we take this branch. So sum of the prefix length, which is 8 plus 16 is 32. Alright, so you can take any branch and the sum of the prefix length from the root to the leaf is always 32. And the first bit in node's effective prefix can never be a mismatched bit. So in the route insertion algorithm, you will never encounter a scenario where you would have to split the node at the very first bit in the effective prefix of any node in the mtry. I leave it to your analysis that why it is so. Alright? So guys, now let us begin with the route search algorithm. So you can see that we have an mtry data structure on the right hand side, and at this point of time, these 5 routes have already been inserted into this mtry data structure. So it simply means that we have inserted 5 routes. It means this mtry data structure would have 5 leaves. Now we will going to discuss how to search a particular route in this mtry data structure. So when I say searching a particular route, it means that given a route, let's say 128.128.0.0/16, I need to come up with the answer yes or no whether this route is present in this mtry data structure or not. So route search algorithm is based on exact match bit by bit, including the don't care. So for example, if I am looking to compare the bit 1010 with the bit pattern 101x, and if I ask you the question whether these 2 bit patterns are equal or not, or whether these 2-bit patterns exactly matches or not. The answer is that they do not matches. And the reason is simple. The last bit here is 0 and here the last bit is a don't care bit. So exact match means that each bit between the 2-bit patterns which are being matched must exactly match. Even the don't care bit has to match exactly with the don't care bit on the other side. So for example, let's say another example, we have a bit pattern here 101x. Does it exactly match with the bit pattern 101x? And the answer is yes. Alright, so exact match means that even don't care bit has to match exactly with the complementary don't care bit on the other side against which the comparison is being done. Having said that, now let us see whether we are able to search the route 128.128.0.0/16. So the very first thing that we need to do is to compute the effective prefix of this route. So the following is the effective prefix of this route. Now route search algorithm begins with the root node again. The very first bit of the effective prefix is 1, so I will take a path along the 1th child of the root node and I will land at the node number 3. The node number 3 has a prefix length 8, so I will going to compare the 8 bits of the effective prefix with the 8 bit of the effective prefix of the node 3, and they exactly matches. Alright, so if they exactly matches, then I will continue to traverse the mtry downwards. Now the next bit in the effective prefix is 1, so I will take the path along the 1th child of the node 3 and I will land at the node number 8. And the node number 8 has a prefix length of 24, so I will going to compare the next 24 bits of the effective prefix of the input route with the 24 bits of the effective prefix of the node 8, and I see they exactly matches. Alright, and my entire 32 bits of the input effective prefix has been exhausted, so I will stop my search here. Alright, so it simply means that the node number 8 is a matching node and it corresponds to the route 128.128.0.0/16, which is this one. Alright, so this is how I search a route in the mtry. So I will return true that hey, such a route is present in the routing table. Let us execute the route search algorithm for another example. So for example, let us suppose that I want to search this route in this mtry data structure. So again, convert this route into its effective prefix. Now start your search from the root node again. Since the first bit of this effective prefix is 1, I will take a path along the 1th child of the root node and I will land at node number 3. The prefix length of the node number 3 is 8, so I will going to match 8 bits of the route that is being searched with the 8 bits of the effective prefix of the node 3, and they exactly matches. So I will continue my search down the tree. The next bit in the input effective prefix is 0, so I will take the path along the 0th child of the node 3 and I will land at node number 7. The node number 7 has the prefix length of 8, so I will try to match the next 8 bits of the input effective prefix with the 8 bits of the effective prefix of the node 7, and I find that they exactly matches. So I will continue my journey downwards. The next bit in the effective prefix of the input is don't care, so I will take the path along the don't care child of the node 7 and I will land at node number 6. Now the prefix length of the node number 6 is 16, so I will going to compare the 16 bits of the input route with the 16 bits of the effective prefix of the node 6. Alright, and they exactly matches, and my input effective prefix has been completely exhausted, so I will stop at node number 6. So it would simply means that the route is present in this mtry data structure, and the node which holds the data corresponding to this route is the node number 6. Alright. Similarly, if I want to search the route 128.128.0.2/32, Then again compute the effective prefix of this route and start your search from the root node of the mtry. Since the first bit of this prefix is 1, so I will take a path along the 1th child of the root node and I will land at node number 3, whose prefix length is 8. So I will going to compare the 8 bits of the input effective prefix with the 8 bits of the current node, which matches. Alright, so I will inspect the next bit of the input prefix, which is 1. So I will try to traverse down the tree along the 1th child of the node 3, but the 1th child of the node 3 is null. There is no path. So it simply means that this particular route is not present in this mtry data structure. At any point during the traversal in the mtry data structure, starting from the root node down the tree towards the leaf, if you ever find that you have nowhere to go, then it means that that particular route is not present in this mtry data structure. Alright? Here I cannot descend down the mtry data structure further because the 1th child of the node 3 is null and I cannot reach to the leaf node of the mtry data structure. Alright, so it means that this particular route is not present in this mtry data structure, as simple as that. So you can see that searching a route in the mtry data structure is very simple and straightforward. You just keep on comparing the bits of the effective prefix of the input route with the effective prefixes of the nodes as we traverse down the mtry data structure, and it is mandatory that you should end up with some leaf node in the mtry data structure by the time your effective prefix is completely exhausted. Then only that particular leaf node is the matching node corresponding to your route which is being searched. So guys, now we jump to the route deletion algorithm. For route deletion, exactly opposite approach of route insertion is followed. So for route deletion, we need to locate the leaf node which is exactly matching the route which we want to delete from the mtry data structure. This is the first step. So in order to perform the first step, we need to execute the route search algorithm which we have just discussed. Alright, so it is quite trivial that whatever route you want to delete from the mtry data structure, you first need to locate the leaf node which holds the data for that route in the mtry. Alright, and for that we need to execute the exact match route search algorithm which we have just discussed in the previous lecture video. After that, once the leaf node is located, we simply delete the leaf node. And after that, deletion of the leaf node makes its parent a half node. We already know that in this mtry data structure, every internal node is a node with exactly 2 children. Alright, and the exception is a root node, of course. So the moment you delete the leaf node from the mtry data structure, the parent of the leaf node becomes a half node. Now, our mtry data structure cannot have half nodes, and therefore our mtry data structure has to do adjustment so that the half node that is just created becomes the full node again. Full node means a node with exactly 2 children or without any children. So parent node merges its other child in order to become the full node again. And root never executes the merge algorithm. So this step, we call this step as merge algorithm, which is exactly opposite of split algorithm. Alright, so let us go through the example. So let us go through a couple of route deletion examples in order to exercise this algorithm, and you will find that the route deletion algorithm is exactly opposite to the route insertion algorithm. So guys, now let us go through the example in which we will going to discuss how route can be deleted from the mtry data structure. So you can see that this is the mtry data structure which is already built, because at this point of time these 6 routes have been inserted into this mtry data structure. All right. So now let us delete each of these routes one by one, starting with the first route. So we want to delete a route 1.2.3.4/32 from this mtry data structure. So the very first thing again we will do is to compute the effective prefix of this route. All right. And now let us go through the steps regarding route deletion. So the very first thing that we need to do is that execute the route search algorithm and locate the leaf node which stores the data for this route 1.2.3.4/32. So the exact match route search algorithm will going to give us the node number 9. All right. After having located such a node, simply delete that node. So the node number 9 is deleted straight away. All right. So obviously in the parent node, you will adjust the pointer value to point it to null because the child has been deleted. Now you can see that the node number 2 is a half node. It is a node which has exactly one child, and that is now node number 10. So now we need to fix up our mtry such that the node number 2 becomes the full node. That is the node with exactly 2 children or the node with exactly 0 children. The node number 2 cannot continue to exist as a half node. So the following step is the node merging algorithm. So let us execute these steps one by one. The very first step says that append the effective prefix of the other child, which is the node 10. So node 9 parents is node 2 and node 2's other child is node 10. All right. So append the effective prefix of the node 10 to the effective prefix of the node 2. The effective prefix of the node 10 contains don't care, which is 24 times don't care bits. So the effective prefix of the node 2 would become the effective prefix which it already has appended by the effective prefix of the node 10, which is 24 times don't care. And obviously, since you are merging 24 don't care bits to the effective prefix of the node 2, therefore the prefix length of the node 2 would become 8 plus 24, which is 32. All right. So the effective prefix of the node 2 is 7 times 0, then 1, and then 24 times don't care bits. Then the second step is that transfer the data of the node 10 to the node 2. So here the node 10 has the data which is next hop 1.0.0.0/8, that is pointer to some object in the memory which represents the next hop. So simply transfer this data to the parent, which is node 2. So the data part of the node 2 would become next hop 1.0.0.0/8. That is the next hop of the route 1.0.0.0/8 has been moved from the node 10 to the node 2. Then the next step says break the parent-child relationship between the node 2 and the node 10. That is, this linkage will going to be broken. So node 2's don't care children would become null. All right. And the next step says that transfer all the children of the node 10 to the node 2. So in this case, the node 10 is a leaf node. It do not have any children. Therefore, there will be no transfer of any children of the node 10 to the node 2. But if node 10 had any children, then they would have been moved as a children to the node 2. And finally, delete the node 10 as well. So it will take you a couple of 2-3 times a practice to actually exercise this route deletion algorithm. So don't worry, we will going to delete all these routes one by one from this mtry data structure. So now you must be very eager to see what does the final mtry data structure look like when the route 1.2.3.4 has been deleted from this mtry data structure. So you can see that deletion of a route from the mtry result in the deletion of 2 nodes from the mtry data structure. In this case, the node number 9 and the node number 10. So the final mtry data structure would look something like this. All right, you can see that the effective prefix of the node 2 is now grew from just prefix length 8 to full prefix length 32, because this portion of the effective prefix is coming from the node number 10, which has been merged into the node 2. So again, let us take one more example. Let us delete the route 128.2.3.4/32. So convert the route that is to be deleted into its effective prefix form. Alright, and now execute the exact match route search algorithm, and you will find that the node number 5 is the node which we are willing to delete. It is the node which holds the next hop for the route which is being deleted. So we are interested in deleting the node number 5. So straight away delete the node number 5, adjust the pointer of the parent node to point it to null because its child has been deleted. And now the node number 7 has become a half node, therefore node number 7 will execute the merge algorithm. Alright, so again these steps will be executed. You append the prefix of the node 6 to the effective prefix of the node 7. So node 7 effective prefix would become XXXX 16 times, and the prefix length of the node 7 would become 24, because 16 don't care bits has been transferred to the node 7. Then transfer the data of the node 6 to the data of the node 7. Alright, so the data part of the node 6 would become null. Then break the parent-child relationship between the node 7 and the node 6. So the node 7 pointer needs to be adjusted to point it to null. Now transfer all the children of the node 6 to node 7. So in this case again, node 6 is a leaf node, therefore there is no need to transfer any children of the node 6 to the node 7, and finally delete the node 6. Alright, so the final mtry data structure would be this one. Alright, the node number 5 and the node number 6 has been completely disappeared from this mtry data structure. Now let us go through the next example. So proceeding towards the next example, let us delete the route number 3, which is a default route. So execute the exact match route search algorithm, and you will find that you need to delete the node number 4. Alright, now it is an exceptional case that whenever you need to delete a node which is a direct child of the root node, then you have to do nothing, simply delete that particular node from the mtry data structure and adjust the parent and adjust the child pointer of the parent node to point it to null. Alright, so the final mtry data structure would look something like this. The node number 4 has simply disappeared from this mtry data structure. Alright, the root node never execute merge algorithm. Remember that. There is no need for the root node to execute any merge algorithm. A root node can be half node, it can have one child, it can have 2 children, it can have 3 children. A root node enjoys all the privileges. So guys, now you can see our mtry data structure is gradually shrinking. Now let us continue with the route deletion. Now let us delete the route number 4, which is 128.2.0.0/16. So the effective prefix of this route would be the following. Alright, so using exact match route search algorithm, we would going to locate the node, which is the node number 7, which holds the data for this route 128.2.0.0/16. And as per the algorithm, we will going to delete the node number 7 straight away, and its parent, that is node number 3, would become a half node, so it will execute the merge algorithm. Alright, after executing the merge algorithm, the node number 8 would be vanished, and node number 3 will borrow the effective prefixes of the node 8 such that the node number 3 would have the effective prefix of length 32. The data part has also borrowed from the node 8, which has just vanished. Also, the node number 8, which is just deleted, did not have any children. Therefore, there is no transfer of any children from the node 8 to the node 3, and the node 3 becomes a new leaf node. So this completes the deletion of the route number 4. Then coming to the route number 5, compute the effective prefix of the route 5 and trigger the route search exact match algorithm, which would give you the node number 3. Alright, and now we will simply going to delete the node number 3, and since the parent of the node 3 is a root, therefore there is no need to execute merge algorithm. So the final mtry data structure would be the following. As simple as that. And this completes the deletion of the route number 5. Now let us delete the final route. So compute the effective prefix of this route and trigger the exact match route search algorithm, which would going to give you the node number 2. Alright, so delete the node number 2, and since the parent is a root, therefore there is no need to execute any merging algorithm, and the final mtry data structure would be the following. Alright, so we arrive at the same place from where we began. Our root node enters into the initialized state again. Alright, so this completes the deletion of all the routes from this mtry data structure. So I would suggest that you can rewind the lecture video and repeat and exercise the route deletion algorithm again. So far we have completed the route insertion, the route search, and route deletion. And what is left is the final thing, which is route lookup, which is based on longest prefix match. So this is the next and the final algorithm that we will going to discuss. So guys, now let us discuss our final algorithm, that is route lookup. So you can see on the screen, this is an mtry data structure, which is essentially a routing table. And at this point of time, the following 6 routes has been inserted in this routing table. Alright. So in case of route lookup, for a given IP address, we must give or we must find the route from this mtry data structure with the longest prefix match possible. Alright. In route lookup algorithm, the bits 0 and 1 matches with the don't care. For example, if you have a binary string 1010 or binary string 1011, then we say that these two binary string matches with the string 101 don't care. And following are the examples of the expected result of route lookup. The longest prefix match, that is LPM, for a given IP address 128.2.3.4 must give the route 128.2.3.4/32. So this is the route in this mtry data structure which matches best with the given IP address. Alright, these IP address will be fetched from the IP header of the packet, and the router, after fetching the IP address from the IP header of the packet, look up into the routing table to find the best route that matches that IP address. And once the router finds the best route, then using the next hop information of that route, the router then eventually forwards the packet to the next node in the network. So this is how routing table is used by a layer 3 forwarding device for forwarding the traffic. Similarly, second example is that for a given IP address 122.2.3.5, the best route or the longest prefix match route is 128.2.00/16. Note that in your mtry data structure, if you have a default route installed, then any unknown IP address would always match with this default route as per the longest prefix match principle. Alright, you just take any arbitrary IP address, let's say 10.1.1.1. This route will not match any other route in this mtry data structure, but it will always match with the default route, which is essentially 0 by 0 route. But what is the algorithm which will make sure that for a given IP address, when you look up in this routing table, the lookup algorithm will always give you the route with the best match or the route with the longest prefix match? So this is what we will going to discuss next, the route lookup algorithm. So guys, now let us take an example. Let the router fetches an IP address from the IP header of the incoming packet, and let the IP address is 128.2.3.5, and our objective is to look up into this MTRI data structure in order to find the route as per the longest prefix match principle. So the very first thing that we need to do is to convert the given IP address into its equivalent binary form. So this is the binary form of this IP address, which is a 32-bit address. Now we will parse this 32-bit IP address into this MTRI data structure starting from the root. Now note that route lookup algorithm uses an intermediate data structure called stack. We start our search in this MTRI data structure from the root as usual. Alright, since we are starting our search from the root, in the stack we always push the don't care child of the current node. At this point of time, the current node is the root where we are starting our search from, and the don't care child of the root node is the node number 4. So in the stack, we push the node number 4, and we also push the second thing in the stack, and that second thing is the number of bits of the input string which has been parsed so far while we are traversing this MTRI data structure from top to bottom. At this point of time, we are at the root node, therefore the number of bits of the input string that we have parsed so far is 0. Alright, that is, we are on the first bit. So these are the two things which we need to push as a single entity in the stack: the don't care child and the number of bits of the input string which we have passed so far while we are traversing this MTRI data structure from top to down. So now let us begin our search in this MTRI data structure. The first node of the input string is 1. So we will take the path along the 1th child of the root node and we land at the node number 3. The prefix length of the node number 3 is 8, so we will going to match first 8 bits of our input string with the first 8 bits of the node 3. Alright, and they exactly matches. Now as the second step, we also need to push the don't care child of the node 3, but in this case, the don't care child of the node 3 do not exist, it is null. So no need to push anything into the stack. Alright, and we will continue our search down the tree. So the next bit of the input string is 0, so we will take the path along the 0th child of the node 3 and we will land at node number 7. The prefix length of the node number 7 is 8, so we will going to match the next 8 bits of the input string with the 8 bits of the node 7, and they exactly matches. Because they exactly matches, therefore we will going to push the don't care child of the node 7 into the stack. So don't care child of the node 7 is 6. That is 6th node, and by the time we reach the node number 7, the total number of bits that we have passed on the input string is 8 plus 8, which is 16. So 16 bits of the input string has been successfully passed so far. And after making an entry into the stack, we will continue our search. Now the next bit of the input string is 0. So we will take the path along the 0th child of the node 7 and we land at the node number 5. The prefix length of the node number 5 is 16, so we will going to match the 16 bits of the input string with the 16 bits of the effective prefix of the node 5. And they do not matches, unfortunately. So the moment there is a mismatch, using this stack, we will going to backtrack. So we will backtrack and we will shift our search from the node 5 to the node 6. But how? We will going to pop the element from the top of the stack. So when you pop the element from the top of the stack, it essentially says that we need to begin our search from the node 6, that is this node, and we have successfully passed 16 bits of our input string. So it essentially says that we need to shift our search to the node number 6, and 16 bits of the input string has successfully passed. So we need to begin matching the bits of the input string from this particular bit, because previous 16 bits have already been passed in the mtry data structure. All right. So what we will going to do, we will going to shift our search to the node number 6, because we have popped out this entry from the stack. The entry of the stack essentially tells us that where we have to shift our search in this mtry data structure. So here, after shifting to the node number 6, the prefix length of the node number 6 is 16. So we have to match the 16 bits of the input string with the 16 bits of the node 6, and they matches. All right. So here the entire input string of the input is exhausted. So this is the node where our search ends. So the node 6 corresponds to the route 128.2.0.0/16. So this is the route which matches with our IP address as per the longest prefix match principle, and the next hop of this route that is the data part of the route, will be used for forwarding the traffic. And note that when your route lookup algorithm ends, it is not necessary that your stack should be empty. All right, your stack may have some elements by the time you have found the route of your interest. So you have to discard or destroy the stack which may contain some elements in it the moment you found the route of your interest. All right. So in the stack, we always push the node which is a don't care child of its parent. Whenever there is a no match, backtrack using stack pop operation. Destroy the stack after the search is complete. All right. So we will destroy the stack because we have already found the route of our interest. Let us discuss the route lookup algorithm with one more example in the next lecture video. So guys, now let us take one more example. Suppose we want to do a route lookup for the IP address 1.2.3.5. So convert this IP address into its equivalent binary form, take up the stack, and we will going to start our search from the root node. So the don't care child of the root node is 4. So just push the entry into the stack. The node number is 4 and the total number of bits of the input that has been passed is 0. So here 0 means the beginning of this input string. So now let us begin our search from the root of this mtry data structure. The first bit of the input binary string is 0. So we will take the path along the 0th child of the root node and we land at node number 2. The prefix length of the node number 2 is 8, so we will going to match the 8 bits of the input string with the 8 bits of the effective prefix of the node 2, and they matches. So because they matches, therefore push the don't care children of the node 2 into the stack, which is the node number 10, and the total number of bits that have been successfully passed is 8. All right, and we will continue our search. So the next bit of the input string is 0, so we will take the path along the 0th child of the node 2 and we will land at the node number 9. The prefix length of the node number 9 is 24, therefore match the 24 bits of the effective prefix of the node 9 with the 24 bits of the input string, and sadly they do not matches. Now because they do not matches, therefore we will going to shift our search from node 9 to node 10 by popping the top element from the stack. the top element from the stack says, resume your search from the node number 10, and the total number of bits of the input string that has been passed is 8. Alright, so we are at this bit position in our input string, and we are at the node number 10. Now prefix length of the node number 10 is 24, therefore match the bits of the effective prefix of the node 10 with the 24 bits of the input string, and they matches. Alright, because the effective prefix of the node 10 is all don't care. Therefore node 10 matches. And now after this match, the total number of bits of our input string has been exhausted. Therefore we stop our search here at node number 10. So the route of interest that we are looking for is the route 1.0.0.0/8. So this is the route which will be used by our router in order to forward the traffic which is destined for IP address 1.2.3.5. In other words, we say that this is the route which matches best with this IP address as per the longest prefix match principle. And of course, once the route is located successfully in this route lookup algorithm, we will destroy our stack. Now note that as long as in your mtry data structure you have this default route installed, so it is not possible that for a given any random IP address, if you could not find the route as per the longest prefix match principle, then at the least the default route 0/0 will going to match with any random IP address as per the longest prefix match principle. The node number 4 is the bottommost point in the stack, and when this will pop out of the stack, you will shift your search to node number 4. And when you shift your search to node number 4, the effective prefix of the node number 4 is all don't care. So it means that whatever your IP address is, it will certainly going to match with this route, which is 0/0. We actually call this route with a special name called default route. So this was the IP route lookup algorithm. You may practice it more for different IP addresses and try to look up those IP addresses in this mtry data structure. So I leave it to you to practice yourself. So now let us summarize what we have learned in this course so far. We learned the data structure called mtry, which is a tree-like structure. Each node is a prefix of its children. Alright, so just like you have a name, let's say Abhishek Sharma. So Abhishek will go in the parent and Sharma will go in the child, or something like that, such that each node contains the data which is a prefix of its children. This is the property of this mtry data structure, and for this reason the trie families of data structure is also called prefix tree. Alright, they are also called prefix tree because each node contains the prefix of its children. In other words, every children contains the suffix of its parent. And we learned about the route insertion algorithm, route search algorithm, route lookup algorithm, and route deletion algorithm. All of them takes order of k time, where k is the number of bits in the input string. So for IPv4 address, k is equal to 32. So essentially, mtry data structure gives you constant time complexity.